In section 5.7, we're factoring by special products. The first one we're going to look at is a perfect square trinomial. A trinomial is a perfect square trinomial if it can be written so that its first term is the square of some quantity a, its last term is the square of some quantity b, and its middle term is twice the products of the quantities a and b. So perfect square trinomials look like a squared plus 2ab plus b squared, and it can be factored as a plus b squared, or a squared minus 2ab plus b squared turns into a minus b squared. The nice thing is you don't have to memorize these formulas because you can always just use your regular factoring method and you will get the same answer. So I'm going to show both methods just so you have them. So first is going to be with the Berry method that we've used previously. You always want to make sure that there's no GCF, which in this case there isn't. So A is 1, B is 10, and C is 25. And so when I do A times C, I get 1 times 25, which is 25. We have our two options, 2 positives or 2 negatives, and we know it's 2 positives because B is positive 10. The factors of 25 are 1 and 25, and 5 and 5. And so this last combo is what will give me 10. So you bring down the leading coefficient, which is 1, and we split our m's. We have our plus 5 and our plus 5. And the last step is to divide out anything they have in common. But the only thing they have in common is 1. And we end up with m plus 5 times m plus 5, which is the same thing. So we can write m plus 5 squared. So I didn't use the formula at all, I just used the Berry method, and I'm going to get the same answer if I do use the formula. So the first thing you have to notice is that the first and the last term are perfect squares. And so using the fact that this is in the form a squared plus 2ab plus b squared, which will turn into a plus b squared. Our a is just m, and our b would be 5, because 5 squared gives me 25. And so plugging this into the formula, I end up with m plus 5 squared, which is the same thing I got with the other method. Let's try the next one. 12a squared x minus 12abx plus 3b squared x. First things first is there a GCF? We can pull a 3 and an x out of all of the terms. And what you have left over is 4a squared minus 4ab plus b squared. You're going to want to use the formula on the 4a squared minus 4ab plus b squared part, or you can do the Berry method. I'm going to do both. So our a in this case, which the variables are going to be a little bit confusing, but a is 4, b is negative 4, and c is 1. So when I do a times c, I end up with 4 times 1, which is 4. We have our two options, and we'll be using the two negatives because b is negative 4. The factors of 4 are 1 and 4 and 2 and 2. And we know they're both negative. So the negative 2 and negative 2 will get me to the negative 4. So we still have our 3x on the outside. We bring down the leading coefficient, which is 4, and we're going to split the a's. We use the two numbers we just found, but we're missing that b portion, so we're just going to put that on the back of our 2's. The last step is to divide out whatever they have in common, which is 2 in this case. So we end up with 3x times 2a minus b times 2a minus b, or we can write this as 3x times 2a minus b squared. If we want to use the formula, you still have to take the GCF out first. And so we're still working with 3x times 4a squared minus 4ab plus b squared. And you have to notice that the first term in the 4a squared minus 4ab plus b squared is a perfect square, and so is the last term of b squared. We know we're in the form a squared minus 2ab plus b squared, which turns into a minus b squared. Well, in this case, our a would be 2a, because when I square it, I square the 2 and I square the a, which would give me the 4a squared. Our b is just going to be b, because when I square it, I get b squared. And I know the letters are a little bit confusing because we have a and b in the original equation, but I just want to stick with the same format throughout. So when I plug it into the formula, we still have the 3x on the outside. It kind of just gets copy and pasted along the way. But now we can break down the black polynomial into 2a minus b squared. So you can see in either one of these, we end up getting the same answer whether I used the Berry method or I applied the formula. So if you get stuck, you can always just apply whatever method has worked for you for factoring. The next one we're going to look at is the difference of two squares. And this special product was presented in an earlier section, but it's just the product of a sum and a difference of two terms. And it's a squared minus b squared. It gets factored as a minus b times a plus b. This would be a good one to memorize because we use this one all the time, and it's pretty easy to distinguish from other ones. Whereas the perfect square trinomial, you might not be 100% sure. So again, you can use whatever method you want here. The first step is always to look for a GCF, which we don't have with 16y squared minus 9. So we could go right into the Berry method, or we could apply the formula. So let's go ahead and do the Berry method first. I have a is going to be 16. We don't have a middle term with just a plain y attached to it, so the coefficient of it is 0. And c is negative 9. So when I do a times c, I have 16 times negative 9. Which gives me negative 144. I'm going to have one positive and one negative. And because the goal is to get to 0, we want to find factors that are the same, which in this case would be 12 and 12. Because one positive and one negative, when I combine them together, gives me that 0 that I'm looking for. So again, we bring down the 16 and we split the y's. And we have plus 12 in one of them, and we have minus 12 in the other. And we divide out whatever they have in common. So here they both have a 4 in common. So you end up with 4y plus 3 and 4y minus 3. If I just wanted to apply the formula, I need to notice that I'm missing the middle term and that the first term is a perfect square and the last term is a perfect square. So in this case, my a would be 4y, because when I square it, I square the 4 and the y. And my b would be 3, because 3 squared would give me the 9. So now that I've figured it out, we know we're in this form here. So we would end up with 4y minus 3 and 4y plus 3. And it doesn't matter which way you write this, what order it is, because regardless of multiplication, order does not matter. Let's go ahead and try the next one. First things first is to find if we have a GCF, which we do in this case. We can take a 2 out. And so what I have left over is 25 minus 4y squared. Let's go ahead and just use the formula in this case. You'll notice that the first term, 25, is a perfect square, and 4y squared is also a perfect square. So just looking at this piece, we know we're in the form a squared minus b squared, and that's going to give me a minus b times a plus b. My a in this case is going to be 5, because 5 squared gives me 25. And my b in this case is going to be 2y, because I need to square the 2 and the y, which gives me 4y squared. So we still have the 2 out front. And then in our parentheses, we're going to have 5 minus 2y and 5 plus 2y. So in general, except for factoring out a GCF, the sum of two squares usually cannot be factored using real numbers. The difference of squares is completely okay, but the sum of squares is not. Although the sum of two squares usually cannot be factored, the sum of two cubes as well as the difference of two cubes can be factored as follows. These ones you will need to memorize. So a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. And a cubed minus b cubed goes into a minus b times a squared plus ab plus b squared. So what changes between these two is if the original is a sum of cubes, the first set of parentheses is going to have a plus sign. And then the middle term of the second polynomial is negative, but the rest of it is positive. If we're dealing with a difference of cubes, then the first set of parentheses has a minus sign, and the entire thing has positive in the second polynomial. So let's go ahead and factor p cubed plus 27 q cubed. So we know that the first term is definitely a perfect cube because it's p cubed. But what about the second term, 27q cubed? Can I rewrite this so that when I cube it, I get 27q cubed? Well, the cube part is pretty easy, but what about 27? What number cubed gives me 27? 3 does. So we could rewrite this in terms of cubes as p cubed plus, inside our parentheses, we would have 3q, and that entire thing would need to be cubed because the 3 gets cubed and so does the q, which would give me the original. Now this is a sum of cubes, which means we're going to use the formula. In this case, our a is p and our b is 3q. So using the formula a cubed plus b cubed, we get a plus b times a squared minus ab plus b squared, and we need to just fill in our a and b. So you have p plus 3q times, we've got p squared minus p times 3q plus 3q squared. So let's just simplify this a little bit. We have p plus 3q in the front, and in the second one we get p squared. P times 3q is just going to give me 3pq or qp, it doesn't matter. And then for that last term, we have to make sure we square both the 3 and the q. So we end up with 9q squared. And that is your final answer. We want to do the same thing with this last one. We have y cubed minus 64. So let's go ahead and rewrite this. The first term is pretty easy because we just go ahead and do y and it's going to cube. And then 64, what number cubed will give me 64? Well, the answer is 4. 4 cubed gives me 64. This is a difference of cubes. So we have a cubed minus b cubed is going to be a minus b times a squared plus ab plus b squared. In our case, our a is y and our b is 4. And so we end up getting y minus 4 times y squared plus y times 4 plus 4 squared. And we just want to simplify. We have y minus 4 times y squared plus 4y plus 16. And you won't be able to break down that second polynomial any further because it's prime.